Okay, guys. Last time we
Yeah, is there a solution for this quiz?
there's no solution for the quiz. Just
Oh,
you want solution?
yeah, can you upload that before the final?
Okay. Okay.
Thank you.
Yeah, all of them are basically conceptual and calculations.
Oh, alright.
Yeah. So.
To just scan like hundreds.
Okay. Yeah. Yeah, I'll do that. Okay. So last time we have talked about the uniqueness and existence of the solution of linear equation, and we just started talking about linear space. And this time we will continue talking about the linear space. And the class this week is very important because we are talking about the most important part of linear algebra. Although it's just one of the most important part, but if you don't understand this part well, you will have trouble afterwards. So please keep concentrated in this class. So last time we started talking about some intuition about vector spaces, and I draw on the blackboard about maybe a zero-dimensional vector space, a one-dimensional vector space, which is our line, and a two-dimensional vector space, and three-dimensional vector space. So basically, this is our common sense that no matter who tells us that zero-dimensional space is a point and one-dimensional space is a line, two-dimensional space is a pen, and three-dimensional space is where we live, right? So actually, intuitively speaking, a linear space, you just have to imagine a space which is infinitely large. It is infinitely large, flat space with origin chosen. So to be a linear space, you should make sure that it is infinitely large. So which means that all of those guys are actually extended to infinitely far away, right? So this is a line. This is actually this is not just a segment. It is a line. So I mean it is extended to everywhere else. And this is a infinitely large band, and this is all the spaces. And the second kind of intuition is that we require all those spaces to be flat. So flat just means that it is a straight line, and it is a pen, and it is I don't know how to describe it. So there's no curvature for all of those guys. So everything are straight. And with origin chosen, this part is also important because that those spaces are so-called vector spaces, right? So this basically means that we are going to study vectors. But as you can see, as we learned in the first class, I said that if you have a vectors, you can draw that picture, right? You can draw it here, or anywhere you want. So you can actually move this start point to anywhere you want, and draw a vector that is parallel to your original one, which have the same magnitude, and they actually represent the same vector. So in order to study vector maybe in more clear way, we want to move all those vectors to some point that we already chosen. So as you can see, they all represent the same vector, but instead of looking those three vectors in a different position, we will move all of that in the origin like this, and we will move this one to here. So we will assume that all the vectors is start from the origin So this part is origin. So a linear space basically means that we have to choose an origin in our space to be the start point of all the vectors that we are going to study. So vector space or linear space, intuitively speaking, is infinitely large and flat with origin chosen, right? So this is some intuition. Let's just talk about some examples. Although I didn't make any definitions. Okay, so is this piece of blackboard a linear space? Maybe yes or no. Blackboard is no. Okay. Yeah. I don't know. Now let's suppose that this blackboard is flat. It's not a linear. It is or it's not a linear space. Actually, it's not up to now because it's not infinitely large, right? Then we should actually extend this blackboard to infinitely far away, to maybe to here, to everywhere, and then to everywhere in the universe. But even though I extend it, is this a vector space? No. No, why? Yeah, I should choose an origin, right? If I choose an origin, like here, and I say that this is the origin, then it is a linear space. Okay, so basically speaking, a linear space is infinitely large flat space with origin chosen. Let's make a rigorous definition of this. Definition of what is linear space. Parentheses, right linear space. Alright. So this, you can talk about left linear space and right linear space, and I will say something about this later. A linear space over field F. You can think this part as either maybe rational numbers or real numbers or complex numbers, whatever is a set. D endowed with operation called class and action from F. So which is called scalar multiplication. Scalar multiplication. Satisfying those conditions. The following conditions. Following conditions. Okay. So the conditions for this operation class is that any two vectors we can class them together, right? And so what can we say about this class? Okay, the first thing is that for any two vectors v and w in V, v plus w is also an element in V. Define a unique element. In V. So the first one tells me that I can sum up two vectors. Okay. The second condition is that okay the sum is associative. So V plus W plus another vector, let's call it UV W X Y Z. Maybe I need z, let's call it as v, is equal to v plus bracket w plus z. So this is intuitive, right? If you want to plus 3 vectors together, it's the same as you plus the first 2 of them and plus the third one, and it's the same as you left the first one and plus the last 2 of them together and then sum up it with the first one. Okay, the third one is that this sum should be commutative. So this is nothing to say. It's just a very intuitive restriction. And the fourth one is that there is some vector called zero vector. There exists some vector. There exists a zero vector, which is unity of 0, and such that for any vector v in my linear space, I have the property that v plus 0 vector is the vector itself. So this is nothing to say, and the existence of the 0 vector kind of tells you the existence of the origin. So if you have a 0 vector, then you have the origin, because the 0 vector is an element in the set, and this element represents the origin. So this corresponds to the origin. And the fifth one is that for any vector in V, there exists a vector which is in the opposite direction, a vector called minus V in V, such that if you sum up those 2 vectors, it will give you 0 vectors. It is 0 vector. Okay, so this is nothing to say. It basically tells you that if you have a vector right over here, you will also find a vector which is kind of reflection by this point, right? And then the sum of this is add up to be 0. So those are 5 conditions for the sum. And there are also another operation. It's called scalar multiplication. So which means okay, I'll continue writing. And the scalar multiplication satisfying. Okay. So the first one is that okay, so if you want to yeah, so which means that for any lambda in the field, v multiplied by lambda is an element in the linear space. Okay, so for any element in the field and any vectors in V, this vector multiplied by lambda belongs to V. This tells you that any vector can multiply a constant on the right, because the constant comes on the right. That's why here I call it as a right linear space. Why I do that on the right? Because in the future you will see the linear transformation and the scalar should multiply on different sides. Because I want to write linear transformation on the left, so that's why I put the scalar on the right. You can also put the scalar on the left and call it as a left linear space. But afterwards, the linear transformation will actually get on the right side, which is not people like. So that's why I call it a right linear space. But actually, up to now, either left or right doesn't matter because the multiplication for numbers is commutative. you will see in the future if you have non-commutative case and if you want to make analog of the knowledge of linear algebra to other knowledge, you will see to distinguish the right linear space and the left linear space will make a big difference to simplify everything. So up to now, I will say the lambda is multiplied on the right. Okay, so the second one is that if you actually add two scalars together, okay, I will for any lambda mu equals to f, v equals to v. Okay, and this vector multiply lambda plus mu is actually equal to v multiply lambda plus v multiply mu. This is very easy to understand. Just like you have a vector, and then you suppose that this part you enlarged by lambda plus mu, and then it is the same as you magnify that by the constant lambda and magnify that by the constant mu, and sum everything together. So there's nothing to say. And the third one is that, okay, I'll just write everything down because everything is intuitive. V multiply lambda mu is equal to multiply mu. Okay. V multiplied by 1 is equal to V. Last guy is for any lambda in F, V W V plus W multiplied by lambda is equal to V multiplied lambda plus W multiplied lambda. Okay, so if a set endowed with two operations satisfy those conditions, we will call it as a linear space. And every conditions over here is intuitive, but this is a rigorous definition of what is a linear space. Why do we need such a rigorous definition? Because we want to make analog from the linear space that we saw every day to the abstract linear space that we are going to study. Because as you can see, the reason why you study linear algebra, I believe is not like to you want to study the space or you want to study a plane, but you actually want to study other object, which is actually similar to the geometric object, and you want to use the tool of linear algebra to study it. So that's why we make those rigorous definition to actually pick out those objects which we can study using linear algebra, right? And those objects are actually, firstly, it should be a set, and then it has to have an operation which should be similar to the vector addition, and also should have some scalar multiplication, which is similar to the scalar multiplication on vectors. So this is basically the definition of the linear space. And there's basically maybe nothing to say about that because everything is intuitive. Okay, so as I explained why I call it as a right linear space, because if you see the reason I already explained the reason. The first reason is that I said that the linear transformation and the scalar should actually come on the different sides. So that's why I want to put the scalar on the right and linear transformation on the left. Actually, you will also see the reason from the previous knowledge we have already learned, which is if you look at the different textbook, you will see that other textbook will just view vectors as column matrices, right? And the column matrices actually admit the scalar multiplication on the right. Because the column matrices, the set of that is n by 1. And then the only kind of matrix multiplication that it can multiply with 1 by 1 matrix is when I put the scalar on the right. So that is a right linear space. And for the column matrices, the linear transformation is like to multiply a square matrix or another kind of matrix on the left. So you can kind of see this kind of phenomenon from the column matrices, right? So yes, yeah, in the column matrices, if you want to multiply it with a number, the number should come on the right. And if you want to multiply with a large matrix, the matrix should be on the left. So that's basically why I put this scalar on the right. And you will see in the future that if I put the scalar on the right, it will be very convenient for most of our notations. Okay. So far, so good. Okay, now let's look at the examples of vector spaces. So basically, in this class, I will often use 4 examples to demonstrate everything as to use it as example on everything. So let's look at the first example, which is just comes from the geometry. So the first example is the actual vector space. Example 1, the actual vector space. Which is just over R, because we live in the space over R, right? So what I mean by those actual spaces just means those kind of spaces, either a point, a line, a plane, or infinitely 3-dimensional space, or 4-dimensional, 5-dimensional, and higher dimensional that you can't imagine, right? And all of that space, I call it as the actual vector spaces. And because it admits the scalar multiplication by real numbers, so this linear spaces is actually over real numbers. So as we can see, for this kind of actual linear spaces, if you imagine this blackboard with an only intrusion and assume that this blackboard extended to everywhere else, so you can actually see those axioms are actually true, right? Because you have vector addition, which is given by the parallelogram law. If you have 2 vectors, then you will move this vector, you will move the start point of the second vector to the end point of the first vector, and then make a parallelogram, and then add them together. So this is a vector addition, and it automatically satisfies those 5 conditions, right? And it also have like the opposite vector, which is for any vector, you have opposite vector. And you also have the scalar multiplication, so which is just magnify this vector by certain scalar, right? And as you can see, all of those conditions is true. And this is the 0 vector. So this is the actual linear space in our world, right? So actually, those vectors, they are just vectors. Up to now, you can't count them as maybe some numbers. You can't say it's 1, 0 or 0, 1, because actually they are not, right? They are just vectors over here. So this is an actual linear space. And any question?
When you define an origin, do you also define the axes?
No, no axes, just vectors. Just a plane with origin chosen, and you draw a vector. Okay.
So the line in the middle is called 0 vector?
Yeah, because this is what I already chosen, right? And this place is the 0 as 0 vector. Okay, this is the first one. Question?
Sorry, this is kind of a weird question. When you say like the actual vector space, as opposed to what?
You mean a symbol for that?
I mean, how else could you? I
How-
guess you define it in the way that.
I didn't define it. I just said it's a line or pen or three-dimensional space without code. I mean, I only choose the origin, but I didn't choose any axis.
I guess this question is like, what other space is possible other than a vector space? There's no other option.
Other vector space? Yeah, I will give you four examples. And in the future, you will learn the word isomorphic, which means you can actually classify the vector spaces which are basically the same together. So there are infinitely many vector spaces, but afterwards you will see you can use isomorphism to see something. Okay, so this is the first example, which is the actual vector space, which is very abstract when I want to represent that, but it's very straightforward when you think about that. Okay, the second example is the example 2 is all n×1 matrices over R. So I will denote the set of all n×1 matrices over R as n, capital N, which means matrices n×1 bracket R, or I can also denote it as Rn. Yeah, in some book, this notation is most commonly used. So this is the second example. So basically, what are elements in the set? The element in the set, let's say n is equal to 3, right? Then it is the set I mentioned over here is R3 or 3×1 matrices. The element in this set, it looks like something like 3, 1, 2 or 1, 1, 3, and any kinds of those color matrices. And this set is actually a linear space. Why is that? For a set to be a linear space, we need to choose two operations. So the first operation is addition, and the second operation is the scalar multiplication. But this n×1 matrices, it already have addition by itself because we can add two matrices together because they are of the same size, and they also have the scalar multiplication, and which I mean is that I can multiply the scalars on the right. So it is actually a right linear space, and as you can see, it satisfies all those conditions. And so, what is the zero vector in this linear space? Yeah, what is origin in this linear space? Yeah, 0, 0, 0. Yeah, 0, 0, 0 is the zero vector. Right? Yeah. Okay, and the addition is just you add those matrices together, and the scalar multiplication is just multiply these matrices by the scalar, and it satisfies all the conditions. Another question? So this is the second example, which is basically the most of the textbook used as linear space, and they denoted as Rn. Okay, so the third example is maybe the polynomials. Polynomials with bounding grid. Polynomials with bounding grid. Okay, those examples are things like I denote this set as P and set X, which means the variable is X. And I put the 2 over here means I'm considering the polynomial that have the degree at most 2. So the element of this set are of this kind of form. So which is it's a collection of all the polynomials which have the degree at most 2. So it's ax squared plus bx plus c, where all those coefficients are real numbers. So this is actually a linear space. Why is that? Because if we have 2 polynomials, you can simply add them together, and this addition obviously satisfies those five kinds of conditions, right? And we can also do the scalar multiplication, because in the future study, I want to think it as a rectilinear space. In the meantime, you can also think it as a rectilinear space, but actually, because I want to make everything consistent. So currently, I think it as a rectilinear space. And if you have a vector, and if you multiply by a constant, I will define it just to be lambda x squared. And by
we put the lambda on the right.
why did I put lambda on the right?
So this is what you kept on reinforcing the fact that it has to be multiplied on the right.
Yeah.
So why don't you put lambda on
this is our custom notation. Or you can maybe in the future I will just press it like this. But if you can get used to that, I will write like this. Or other way, I will treat it as a left linear space. But I just want to study a linear space on one side. So yeah, because it doesn't matter, because you multiply 2 numbers together, it's no matter which order you take. So I can also write like this. Okay, so you have a scalar multiplication, and you have addition, and you also have the opposite vector, in which here the vector just simply means a polynomial, and the opposite vector of a polynomial, you just take the minus on the whole polynomial, right? X squared plus 2, this is your vector, and the minus of the vector is just minus bracket x squared plus 2. Okay, so what is a zero vector in this linear space? Zero polynomial, right? What is zero polynomial? So a polynomial is, you can treat it as functions, right? A zero polynomial is a function that no matter what your x is, the value of that is always 0. So this one is called a zero polynomial. So if you plug in 1 is 0, if you plug in 2 is 0, and all the way 0. So the zero vector is zero polynomial. Zero polynomial. Okay, this kind of linear space is also a very important linear space, which gives us a lot of examples on linear spaces, and we will use this kind of example to study to study everything in the future. And the last example I want to say is rational functions with fixed. Okay, the name of that is very long, but doesn't matter. Rational functions. Okay, don't scare by the name. I will tell you what's that. So that's basically those kind of guys. So I can write it as like px squared over x minus 1, x minus 2, x minus 3, and they are just the collection of those guys of this ax squared plus bx plus c over x minus 1, x minus 2, x minus 3, where ABC belongs to R. Right? So there are no difference with the polynomials, but just add a denominator on the bottom. And you require that the degree of your denominator should actually be larger than the degree of your numerator. And typically, we will study the space that the degree of the numerator is at most exactly less than 1 of the degree of the denominator. So we will see that in the future. And this is also an interesting linear space because you have saw in the previous class they actually kind of study how to split fractions. And afterwards, I will tell you why that kind of method is true. And actually, I will tell you maybe a faster method to split those kind of fractions. So those 4 examples are basically the examples that we are going to study. So in this example, what is the 0 vectors? 0, yeah. There is 0 polynomial over x minus 1, minus 2, minus 3. 0 vector is 0 polynomial. And yeah. Any other question about those 4 kinds of linear space?
Is the origin and the 0 vector the same?
Yes. The 0 vector is some element in a set, right? And that element is also called origin. Okay, everything is conceptual, so it's not hard. So basically, what are we want to do? We study linear algebra, and basically the linear means the linear combination, right? So we want to use linear combination to simplify everything. So we are going to see what is linear combination and we want to describe a linear combination. So as you can see, there are actually infinitely many vectors in your linear space, right? You can just magnify that by some scalar, and you can add them. You can do whatever you want, and there seems to be infinitely many vectors. But we actually want to simplify the question because most of the question that you are going to study is linear, which means whatever, right? But so the thing is that if we can write every vector as a linear combination of maybe finitely many vectors, we are going to simplify the question of treating infinitely many objects as just treating finitely many vectors, because you can write every vector as a linear combination of some finite vectors. So that's why we want to study what is linear combination, and we are going to make some definition on a bunch of vectors. Okay. Firstly, let's look at an example because we already know what is linear combination in the previous class when we studied the column space and row space. But at that time, we don't know what is linear space, but still we call it as a space. And we kind of see that the linear combination is just multiply each vector by some constant and then wrap them together. So basically, all the examples that we studied previously is in the example 2. So for this example 2, this kind of linear space, we already know this kind of space very well because the only thing we do is to multiply by some numbers and calculate the summation, right? So let's look at any other kinds of examples about the linear combination. I will erase that. Okay, let's say example, the first example. How do you see? So if you imagine the actual two-dimensional space, which is the extended plane with an origin chosen, right? And if I choose two non-collinear vector, and I said that, okay, if V is
What's non-collinear?
non-collinear just means they are not lies in the same line. It's two-dimensional. It's a plane. It's a plane with origin choosers. Origin choosers. And let V and W be two non-collinear vectors. Okay, so what's my conclusion? I say that every vector in the plane and every vector in the plane can be written as a linear combination of these two. As linear combination of V and W. Is that true? Yeah, that's true. Why? This gives you an idea of what is linear combination. So you have two vectors which is not collinear, right? So let's say I give you arbitrary vectors, and think about how do you represent as a linear combination of those two. So suppose I have vectors right over here, right? Then how do you represent this into a linear combination of those two vectors? If you can draw something on the graph. Yeah. Actually, as you can see, you can just imagine that what is a linear combination of those two vectors? A linear combination means that you multiply this vector by some constant and sum up with you multiply this vector by some constant, which means you are only allowed to go in two directions, right? You are only allowed to reach this point by going through two directions. One direction is like this, the other direction is like this. And how far you go is not restricted because you can multiply by a scalar, right? So then you actually just want to find a method that you only allowed to go this direction, but you want to reach this point. What do you want to do? So actually, if you through this point put a parallel line over here, and then such that this line is parallel to this, right? And you just make it longer to this point, and then you can reach this point by going this way, right? You go this way, and you go that way, and you reach this point. And you only went by two directions, which is a direction the same as the first vector and the direction the same as the second vector. Because you are in the same direction with those two vectors, so you just record how far you go in the first direction, and then divide by the magnitude of your first vector. Then you will know the scalar to put on the first vector. Let's say it as lambda. And in the same direction as the second vector, you record how far you go, and then you divide by the magnitude of the second vector, and you will know the constant that's going to multiply on the second vector, right? Let's say it as mu. And then this vector, which I put over here, let's call it as z, or any, maybe let's call it as z. Then z is equal to the first vector multiplied by lambda plus the second vector multiplied by mu. So in this kind of sense, I can use this method to reach every vector in the plane, right? So that basically gives you intuition that every vector in the plane can actually represent as a linear combination of those two guys. So how about the zero vector? How can I combine zero vector from those two guys? Yeah, 0, 0. You multiply the first vector by 0, you multiply the second vector by 0, and sum up them together. Which means you are lazy, you don't want to go, and you will stay here. Okay, so this is the first example. As you can see, these two vectors is able to give every vectors in the plane by linear combination, right? So does every pair of vector could do this? No. Okay, so what is a counterexample such that two vectors cannot give us the whole plane? So example, let's call it one negative. Right? Okay, so if V is a pen with, okay, I don't want to write it again. It's origin intrusion. And like my two vectors, which is so-called V and W. V and W be two vectors, but now they are collinear. Okay, so are they able to represent all vectors in V by linear combination? Okay, let's draw the graph. So here my V and my W is actually collinear. Are they able to represent every vector? No. Why is that?
The directions.
Yeah, because of the directions. As you can see, in this method, why can you reach every point? Because you are actually allowed to go in two directions. But in this example, the direction of V and W are the same. So you're only allowed to go in one direction, although you have two vectors. Which basically tells you that although you have two vectors, the position, the direction of these two vectors actually matters whether or not that you can actually go to whatever you want, right? So in this case, so the second question is that what are all possible linear combinations of V and W? A line that is in the same direction with this vector, right? Question? Okay, yeah, okay, good. So the vector that it can represent is only the vector on this line. Because you are only allowed to go in this direction. You are not allowed to go any other directions. So in this case, these two vectors cannot give us any vectors by linear combination. Okay, so as you can see, although there are two vectors, there are two different cases. Okay, I will just do another kind of example. Let's do something using this example too, right? Okay, use this one. Let's call it example 2 positive. So if my linear space is R2, which is basically consists of those guys, and if my vector V occurs as maybe V is equal to 1, 0, and W is equal to 0, 1. So can we get every element in R2 by linear combination of the linear combination of V and W? Yes or not? Yes. Why is that? Because, yeah. Yes. Are they perpendicular?
There I was.
There's no graph for this.
Yeah.
Because this is just numbers. Okay. So why is that? Because every element is like the form, like some element over here and some element over here. And then the coefficient that you are going to take in each of these vectors is just appeared over here, right? 3, 5 is equal to 1, 0 multiplied by 3 plus 0, 1 multiplied by 5. And for any other vectors, if you want to get maybe 10, 100, you just copy the coefficient here and here, and then your equation becomes true. So in this kind of sense, every vector in this space can be actually written as a linear combination of these two guys, right? So it's similar to the example 1 positive. Okay, let's see the negative case. Example 2 negative. So the same setting as what happened before, but now I write my V and W as two other kinds of matrices, like V is equal to 2, 3, and W is equal to 4, 6. Are they able to give any element in this R2? No, why is that? Oh, they're collinear. Okay. How do you see that? Okay.
Because there's scalar multiples.
Yeah. This one is a scalar multiple of the first one by 2. So why is that? Because as you can see, I can multiply the first guy by C1, and then end up with the second guy multiplied by C2. And finally, you will see that it can't represent every vectors. Why is that? Because the second guy is a scalar multiplication of the first guy. So actually, you can simplify this equation as 2, 3, C1 plus 2, 3 times 2, C2, right? And actually, the fact is that you can factor the same thing on the left, and the rest thing on the right is C1 plus 2C2. So you continue 2, 3 bracket C1 plus 2C2. So that tells you that although you are combining two vectors, but only one vector is effective, right? And then you can just name it as C3. You can call it as C3, and every vector that it could represent is just like 2, 3 times C3. So in this way, they are not going to represent every vector, because any vector of this form must have the property that the second coefficient is 3/2 of the first coefficient. So like it can't represent this guy, right? It can't represent 0, 1. Because if the first one is 0, then 2 times C3 is 0, which makes C3 have to be 0. And then if C3 have to be 0, then C3 times 0 should also be 0. So the only case is that this one is 0, 0 instead of 0, 1. So this 0, 1 is not nice, cannot written as a linear combination of these two guys. Okay, and there are also, you can also give examples using the linear spaces in the example 3 and example 4, whatever. But actually, it tells you that if you have a bunch of vectors, the elements that it could represent by linear combinations is different, right? Like in this example, you have two vectors. You can actually represent every vectors in your linear space, but in this example, you can only represent only few of them. So what is the difference, and how do we describe it? And we call this as we call the set that bunch of vectors could represent by linear combinations as the span of those vectors. So let's write the definition of span. No, this one or not? Okay. Let's call the definition. linear space. And let's call it V1, V2, and finitely many vectors are finitely many vectors are just a set of vectors. So a set of vectors. And the span of these vectors is the span of those vectors is the set consisting all possible linear combinations of those guys. And in this case, we denote it as this set as the span of SPAN and parentheses V1, V2, until Vm. And we use the comma to separate each of those guys. And this is basically a set. So what is the element of this set? The element of this set is all the possible linear combinations of those vectors. So this is what we call span. So, and in the previous example, we can use this kind of notation to denote what happens. But in this example, what is the span of V and W? The span of that is actually it is a set first, right? And what is a set? The set is actually consisting of all the elements that look like this. But the element looks like this could actually simplify as a form that the element looks like this. So the element in the span of V and W are element looks like 2, 3, 2C, 3, or I just call it as 2C, 3C, or maybe 2T, 3T, whatever you like, in which T is real numbers. So a span is basically all the linear combinations of those vectors. So what is the span of this? In this case, what is the span of V and W? What is the span of V and W? The span of that is basically everything, right? Because as you can see, you can actually, everything could be written as a linear combination of these two vectors. So the span of these two vectors is actually everything. It's R2 itself. A dash line? Huh? Oh, sorry. Any question? Okay. Any question?
Is there any limitation for V1 to Vm to be collinear only?
There's no restrictions for them. If you have a bunch of vectors, you can always talk the span of that. Okay. Although some of them might be redundant. Like in this case, the span of those two vectors is equal to the span of just one vector of them, right? Because some of that is redundant, and we will talk about that later. So basically, what I mean is that there's no restrictions on those bunch of vectors. You can basically talk about what is span. Okay, so this is an example of of this kind of notation the span of those vectors. So now let's look at still the notation stuff, but I will say something about matrix. As you can see, you want to talk about linear combination, and you are going to write all these kind of forms like v1 multiplied by some constant plus v2 multiplied by some constant plus whatever v3 multiplied by a constant, right? Okay, because we don't want to write plus and cross everything in our life, so that's why we kind of use the matrix multiplication to simplify this notation, right? Because if you think it as a matrix multiplication, remember previous I told you that in a matrix, you are not only allowed to put numbers in that, you can basically put everything if you can define what is multiplication. So actually, in this case, you can write it as v1, v2, v3, and a1, a2, a3, right? So this basically tells you, if you want to do matrix multiplication, it basically tells you v1 times a1 plus v2 times a2 plus v3 times a3. And this kind of notation is very good. Why is that good? Because the matrix multiplication is associative. And you will see this kind of notation is going to simplify a lot of things that you want to say, but you can simply use a notation, an equation to link everything in an equation. So this is the notation that we want to use. Is that this kind of notation represents this kind of expression. Any question? Okay, so we set two notations, and okay, let's do some examples of such a notation. Let's just say, okay, so I have a linear space, which is maybe a plane with an origin to Z, right? And then now I can draw vectors on that, right? I can draw one vector, another vector. Okay, so what's this? What's that? It's just the vector itself, right? Some people might say it's 1, 0, it's 0, 1. No, who told you that, right? Why is 1, 0? There's no 1, no 0, but just two vectors, right? So you can give it any name. So you can just call it a small face, right? And let's call it as a cry face. Okay, you have two vectors on your blackboard, and it is a vector space. We can do addition, we can do multiplication on those spaces, right? So actually, a small face, because some people told me that they want to use 1, 0, and 0, 1, and they can't get used to this kind of thing, right? Okay, if you want to do that, let's just do this. As you can see, this small face, right, is equal to the small face times 1, right? Because by the axiom of linear space, a vector multiplied by 1 is a vector itself. So this equation is valid, right? Okay, and then it's also equal to this add a 0 vector. Because by the axiom of linear space, any vector plus a 0 vector is a vector itself. So this equation is still valid. And a 0 vector can be written as a cry face multiplied by 0. Because the axiom tells you that 0 vectors, any vector multiplied by 0 is a 0 vector. So you can write this way. And all of the equation is valid, right? And then if you put that into a matrix form, you will actually get a snail face and a cry face multiplied by 1, 0. So in this sense, you can tell it this is equal to bracket small face, crack face multiplied by 1, 0. And by the same reason, this one is equal to the small face, the crack face multiplied by 0, 1. Okay, in the most of the textbook, they want to simplify everything. So in this sense, they always ignore the basis and just write it as 1, 0 and 0, 1. There are several advantages if you ignore the basis because you can write everything in a more clear way. But there's also disadvantages because if you don't put if you do not put those bases on the left, you will feel very, very uncomfortable when you're studying the things like change of basis. Maybe you will misunderstand what is going on, what happened. So that's why I just put those bases on the left and then make everything into the equations. Any question about the notation? Okay, so and then what is a vector like small faces, crack faces multiplied by 1, 1? What is that? Can you draw that on the blackboard? I know I will draw that. Yeah, this guy is equivalent to say the small face multiplied by 1 plus the crack face multiplied by 1. So simply those two vectors add together. So you just add those two vectors, and then this guy is equal to the small face, the crack face, 1, 1. So those are notations, and those are basically what I mean by this kind of form. Okay, and this definition can also be written as this kind of form. The span of that is a linear combination of all those vectors, right? So I can now write this set as a set. It's equal to the set of v1, comma until vn, multiplied with a1, a2, an, in which the a1, a2, an are all numbers in real numbers. So this is basically what the set looks like, and this is also why we put parentheses over here, because you just view this as the same as here. You don't want to put like this guy, right? Because I don't want to think it as a set. I just want to think it as a matrix of vectors that are here. Okay, we talked a lot of notations. Any other question about notations? I think notations is not hard, right? The only hard part should be what is linearly dependency and what is linearly independency. This is most hard part based on the students last summer, right? Some students come to my office before the final exam and ask me what is linearly independence, and I feel nervous. Independence. Okay, let's say what is linearly dependence. Okay, without talking about the word, I will just still look at the examples that are here. Because, as you can see, if you have two vectors, what kind of space that you expect it to span? A plane, right? Because as you can see, if you have two vectors, right, you can actually put it in the general position such that they can actually span a plane, not only a line. So this means we want to make those vectors, make the use of those vectors as big as possible. And that's why we kind of study linearly dependency and linearly independency. So geometrically speaking, the linearly dependency is that when a bunch of vectors cannot make the space as big as we want. So if we have 3 vectors, that is if we have 3 vectors restricted on the plane, then they are linearly dependent, because we are kind of expecting those 3 vectors could give us a 3-dimensional space. But if they are all on the plane, then we can't do that, because the span of these 3 vectors is only a 2-dimensional space. And if we have 2 vectors and if they are collinear, they are called linearly dependent, because we are kind of expecting them to have to give us a 2-dimensional space, but it failed to do that. So this is basically the geometric meaning of linearly dependence and linearly independence. Let's just keep looking at the first example about, so what can we say about the linearly dependence? As you can see, the first thing we saw is that they fail to give us the space as large as we want. So let's talk about linearly dependence. Linearly dependence. So the first intuition we want to call what is linear dependence is that n vectors fails to give us n-dimensional space. Okay, just look at this example. We have 2 vectors right over here, but the only thing that it gives us is 1-dimensional space. So what happened? As you can see in those calculations, the only thing that makes us able to simplify those expressions all the way down to this is the fact that I can write this vector as a linear combination of other vectors. So the philosophy is also true for any other example. So for example, suppose I'm working in R3, which is 3 by 1 matrices, and if I tell you 1, 1, 1, 1, 2, 3, and maybe 3, 5, 7, as you can see, what is the span of that? I mean, how many dimensions do you have? Yeah, 2. Why is that? Because actually, if you want to think about all the possible linear combinations of those 3 guys, we will see actually the last guy is the first guy times 2 plus the second guy. So that's why the space collapsed, right? Because you know that 3, 5, 7 is equal to 1, 1, 1 multiplied by 2 plus 1, 2, 3 multiplied by 1. And then multiplied by C1, C3, right? Maybe not. This multiplied by 2 and this multiplied by 1, right? Okay, yeah, it's right. Okay, 1, 1 multiplied by 1 plus 1, 2, 3 multiplied by 2. And then you keep everything here. So it's 1, 1, 1, C1 plus 1, 2, 3, C2 plus all the guys over here. And then after your simplification, you will get 1, 1, 1 multiplied by C1 plus C3 plus 1, 2, 3 multiplied by C2 plus 2C3. So they are actually a linear combination of 2 vectors. So the reason that they fail to give us the space as large as we want is because some of the vectors is not working. It's because some of the vectors does not give us a new direction or a new dimension. Because the vector 3, 5, 7, the direction that it gives us could be actually represented as a linear combination of those two guys. So it doesn't give us any new dimension or any new directions. So this is the reason why they fails to give us n-dimensional space. So actually the reason is right here. The reason that it fails us to give us an n-dimensional space is actually the same as saying that, can I erase this part?
No.
Okay, copy it. Yeah. Because I want to write everything together. Okay, the reason is that sum of the vectors could represent by others. A linear combination of others. Okay, and these two are actually equivalent, so they are vice versa. So they fail to expand the space as we want. It's equivalent to say, or essentially is the same as sum of the vectors can be represented by others. So what is the second guy tells us? The second guy tells us that there are some relations, like over here, like the 3, 5, 7 is first one times 1 plus the second one times 2. And actually, we said some vector is redundant, but it's redundant. So let's say if I have 3 vectors, right? If I have 3 vectors like this on the blackboard, you can say either of them is redundant, but you can't take all of them away. What I mean is that someone is redundant, then you just take out of that. Then the rest 2 of them maybe is not redundant. So so you can call all those 3 vectors as redundant vectors based on the collection of these 3 vectors is linearly dependent. So actually, the thing that we describe the redundant vectors is like we can write this vector as a linear combination of those 2. And we also want to say, is this vector redundant? Can I just take this vector away and then the rest of 2 can make sense? Or can I just take this vector away? So we just saw one relation, which is that the 3, 5, 7 is equal to the 1, 1, 1 multiplied by 1 plus 1, 2, 3 multiplied by 2, right? So I also want to ask, can I just write 1, 1, 1 as a combination of other 2? Yes, you can. You just move this part to the other side and move this part, or you just move this part to the other side. So you also want to write 1, 1, 1 equal to 1, 2 equal to 3, 5, 7 multiplied by 1 plus 1, 2, 3 multiplied by -2, right? This equation is obtained by moving this part to the left-hand side. And this part becomes here, that part becomes here. And then you can also do, okay, I want to write 1, 2, 3 as a linear combination of those 2 guys. And then what you do is that you move this 1, 1 multiplied by 1 to the left-hand side and divide everything by 1/2. So you can say, okay, 1, 2, 3 is equal to 3, 5, 7 times 1/2 plus 1, 1, 1 multiplied by -1, right? Okay, so why do we write so many equations like this? Why don't we just put all of those guys in just one equation? Like just if you learn geometry, you know that in the high school we learned the equation of a line like y is equal to something x. But afterwards, you want to put everything to one side and make the right hand side to be 0. Which means that instead of writing so many equations like this, we can just put everything to the one side and then make everything to be 0. And the first equation is, I can write it as 357 multiplied by the -1 plus 111 multiplied by 1 plus 123 multiplied by 2, right? And this guy gives us the 0 vectors. And this equation basically can tell us either one of them. So this means instead of repeatedly using this kind of form, in the future we will use this kind of form to represent a linear relation. So what is a linear relation? A linear relation is simply for a bunch of vectors that you can multiply each vector by some scalar multiple such that the sum of that is equal to 0. And this is called a linear relation. Okay, a linear relation, say it again. It's just the means some coefficient such that if you multiply each of the coefficient to the corresponding vectors and sum up all of them together, you get 0, 0, 0. In other words, a linear relation is a way to represent 0 vectors into a linear combination of those 3 vectors. The first one and second one?
The second one.
Second one is that the linear relation is a way to represent 0 vectors into the linear combination of those bunch of vectors. Right? Any question until now? Okay. As you can see, of course, at least for the 0 vector, we can always represent the 0 vectors as linear combination of no matter how many vectors. What is the coefficient you want to choose? 0. Yeah, so we can also represent 0, 0, 0 as 357 multiplied by 0 plus whatever multiplied by 0 plus whatever multiplied by 0. Okay, this is also a linear relation of these 3 guys, but we call it as a trivial linear relation. So actually, basically the linearly independence tells us a non-trivial linear relation. A non-trivial means not all of them equal to 0. Some of them might equal to 0, but if I got one number not equal to 0, it's called a non-trivial linear relation. So basically, this sentence that some of the vectors could represent by the linear combination of other vectors, I can just generalize this sentence as a sentence that from the information of all those bunch of vectors, because I don't want to make some of the vectors special. So I can rewrite it as there are some non-trivial linear combinations. There are non-trivial linear relations. Those vectors. Right? What's the time? Okay, 2 minutes. And if this happens, right? And there's also another way to interpret is that the way to represent a vector into the linear combination of those guys is not unique. equation of those vectors is not unique. I mean, the way is not unique. Why is that? I still have 2 minutes. 2 minutes. So what I mean by the way is not unique, this is because you have linear relations. Let's see. What I mean is like you have 3 vectors like 1, 1, 1, 2, 3, and 3, 5, 7. Although you can't represent every vector you want in the R3, but you can at least represent some of them in R3. Let's say you want to represent you just want to represent 1, 1, 1, right? 1, 1, 1 is, of course, can be written as 1, 1, 1 multiplied by 1 plus other guys multiplied by 0, right? 3, 5, 7 multiplied by 0 plus 1, 2, 3 multiplied by 0. But this is one way to represent 1, 1, 1 in those 3 vectors. There are also other ways, because you have equations like this. You simply add this equation on that equation. And the left-hand side will keep the same because this is a 0 vectors. And if you add this equation, you will see that this multiplied by 2, this guy multiplied by -1, and this guy multiplied by 2 is also give you the same vector because you just simply add 2 equations. So this is what I mean by the way of represent a vector into the linear combination of those vectors is not unique, simply because you have some non-trivial linear relations. So this flow describes how you understand the linearly dependency. We will talk about that in the next class.
What is the difference between non-trivial and trivial?
Non-trivial just means all the other guys are 0.
Oh.
Non-trivial means some of the guys is not 0. I mean, if this guy is 1, then it's non-trivial. The trivial just means 0, 0, 0 all the time. Non-trivial is any other case, exclude this. And this two equations together. Yeah. This part, add this one to this one. Instead, is equal to 1 multiplied by 1, right?
Yes.
And these equations are like equation. It's 1 equal to 4 multiplied by 2. Okay. Yeah, this guy is equal. Add this guy to that guy. This guy is
I said, are you going to start the
this
homework
guy
class?
is -1.
Oh. Start the homework file, that's what I'm saying.
Sorry, 0, 0, 0.
Yeah. 0 plus 2.
Oh, it's plus, right?
Yeah, so 2 plus 1 plus next one plus 1 plus 2 plus 1 is 1.
Okay.
So that's what I mean by
I see. If it's linear combination, then that's what that means. If it's addition, it's not easy. It's not easy.
Oh yeah, it's not easy because you have to
我也忘记拿错了。我昨天去洗衣的时候，
The other question I have is,
公安界有2
so our two parallel
我
lines.
上面的门没有关起来，敲到我头，好痛，
还痛了。
整个都晕晕的，好惨啊！敲笨了。
学习的人就怕被敲分。
So like a line, let's say like two parallel
我
vectors.
真以为你现在学的是其中
You want to go
的
to here?
Yeah.
Because
就
in your space, you move everything to here.
Oh yeah.
So two
Switch
parallel
the origin.
Yeah, like this.
So they are.
就是戴眼镜，然后
戴眼镜的，
Over there, is that like an and? Like, so
Exactly.
those are the conditions for being
Right.
linearly dependent?
Sure, it's all the same.
有点伤人。
当时你们两个都考
But
8，
like, okay, so let's say we have,
8级。
so if one of them is true, all of the other ones are guaranteed to be true. And one of them makes it. And if it's not linearly dependent, then it's always independent.
Yeah.
Okay.
Either way.
我不用交作业吗？
啊，不用，
我想
想交就交。